All right, they like to ask what conditions about the net force acting on the particle necessary for it to execute simple harmonic motion. And these are the rules. You've got an equilibrium point, and that force is toward equilibrium and proportional to the distance from equilibrium. Whoops. K times x. I'm trying to write F equals negative K times x. Okay, so talk about that, right? It also, by the way, doesn't have to be moving to start with, or start not at the equilibrium. And if you just left some object at equilibrium, it would just sit there and not move. Right? So it either needs to start with a non-zero displacement or a non-zero velocity, or both. But it can't have neither. Okay? Okay, the graph shows how the kinetic energy varies with displacement. Okay, so when our displacement is zero, when we're passing through equilibrium, we've got a maximum. That makes sense, right? And when we're at the edges, we don't have any kinetic energy. Okay, so using the axes above, sketch the graph to show how the potential energy varies with displacement. Well, I'm going to tell you this. The total thing has to add to zero. So our displacement one has to have this much here. And then when all of it's kinetic, it'll have zero potential. And then it's going to go through here. Okay, now specifically too, it's also going to cross this thing. It's going to go through here, right? Because that's 0.3 is half of 0.06, 0.03 is. So it's also going to go through this point, right? So draw yourself a nice curve through those points, right? Because it's got to add up to, at any instant, 0.06, because that's the total energy. Okay, let's look at the next page here. Okay, let's see. The mass of the particle is 0.3 kilograms. Use data from the graph to show the frequency of oscillation is 2 hertz. Okay, we can do this. We know that the total energy is 1/2 m omega squared x naught squared, right? Okay. So what we can do is we can solve for omega, right? If we take omega and divide by 2 pi, that'll be the frequency. Because remember, omega is radians per second. If we divide radians per second by 2 pi, we'll get cycles per second. Okay, so how do we figure this out? Well, here's the mass. Plug that in, right? Total energy is 0.06 joules, right? So plug that in there. And then what's our maximum displacement? I sat there and looked at it for a while. I was like, it can't be done. Except you can read the maximum displacement there. So plug this in for the energy, that in for the mass, that in for your x naught, right? Solve for omega. Omega is going to be somewhere between 10 and 15, okay? And then divide that by 2 pi, and you get something just slight. I got like 2.013 cycles per second, okay? Woohoo!